In the previous video, I introduced the notion of the Sturm-Liouville theorem, and we saw how the Bessel equation can be formulated in terms of an eigenvalue problem using the general setup of the Sturm-Liouville theory. Now, let's try to do the same thing for other differential equations. For example, the Legendre differential equation, which is 1 minus x squared y double prime minus 2xy prime plus L times L plus 1 y equals 0, whose solutions are the Legendre polynomials, have to be cast in the general Sturm-Liouville form, which is ry prime prime plus the q plus lambda p y equal to 0. The moment we do that, the full technology of the Sturm-Liouville theory is available to us. Now all we have to do is figure out a way of writing this as the first term. In this particular case, you can immediately realize that if r equals 1 minus x squared, then r prime is going to be negative 2x. What a great coincidence. So our Sturm-Liouville theory formulation is immediate. So we're going to write this as 1 minus x squared y prime prime plus L times L plus 1 y equal to 0. So now what to do about q and p? There are two options here. You can think of either q equals L times L plus 1. If you choose q equals L times L plus 1, the problem then is there's nowhere to put lambda. Lambda becomes impossible to work into this context. So it cannot be a Sturm-Liouville problem because you don't have any eigenvalues to speak of. So we have to take q to be 0. If we take q to be 0, then lambda is automatically equal to L times L plus 1, because that's the only thing that can stand in for an eigenvalue. And in fact, you have the different order Legendre polynomials that correspond to the different eigenvalues, which means the weight function p has to be automatically set equal to unity. So we have all our eggs fall like that in the basket, and so we can immediately write the Sturm-Liouville theorem. So the solutions of this particular differential equation with lambda equals L times L plus 1 are PL x with the boundary conditions A1 times PL1. Actually, remember that you have this interval to be minus 1 to 1 for the Legendre polynomials. So PL minus 1 minus B1 PL prime minus 1 equal to 0. That's the left boundary condition. And then you have A2 PL plus 1 minus B2 PL prime plus 1 equal to 0. That's the right endpoint boundary condition for that problem, for the eigenvalue problem. And this satisfies integral minus 1 to 1. The weight function is 1 times PLX PMX dx. But this we already know thanks to the Rodriguez formula. It's just 2 over 2L plus 1 delta LM. So in this very nice way, we are able to write the Legendre differential equation as a Sturm-Liouville problem. So let's try a couple more very famous differential equations and write them also as eigenvalue problems. The big disadvantage with having more complicated differential equations is this is not very easy to see. So in the Hermite, for Bessel and for Legendre, it was pretty easy to see how to get this thing to look like a Sturm-Liouville form. But in general, that may not be very easy. For example, if I have the Hermite ordinary differential equation, which is given as yn double prime minus 2x yn prime plus 2n plus 1 yn. So I'm getting cocky here. I am already assuming that n is going to be an eigenvalue and the corresponding eigenvector is y sub n. So in this case, n is the all natural numbers including 0 actually. So I'll call n plus 0. So you have the situation here where you now have to write this as ry prime prime, but you cannot do that. If you try doing it, you'll notice that if I try to write this as let's say xy prime prime, I won't get this 2 ever. So how do you make that 2 happen? Now one way to do this is to actually force this to happen. So what I'm going to do is I'm going to say let there be a function f. Let there be f such that f times yn double prime minus 2x f yn prime plus 2n plus 1 f yn equal to 0, such that I can beat it into the standard shape. Now if I look at a standard shape and I write it out fully, the comparison I have to make is r y double prime plus r prime y prime plus q plus lambda p y equal to 0. Now how do I solve for f? Well, it's very simple. You have a set of conditions now. Don't mess with the lower order terms. We just look at the highest order terms. So I immediately get that f must be equal to r, and that negative 2xf must be equal to r prime. So these two can be immediately solved. So if I r is equal to f, so if negative 2xf is equal to r prime, I'm going to get that's equal to f prime. So I have an ordinary differential equation f prime equal to negative 2xf, which can be immediately solved using separation of variables. That's just df over f equals negative 2x dx, or f equals natural log of f equals negative x squared plus some constant, which I'm not going to worry about. And so this tells me that f is just e to the minus x squared. So that's a magical coefficient. So now I have my Sturm-Liouville theory form of the Hermite differential equation. 2n plus 1 e to the minus x squared yn equal to 0. And then you can write the full Sturm-Liouville Hermite theorem with corresponding orthonormal relations, and I'm not going to bother doing that. So here we'll identify what the q is. The q is going to be 0. The weight function p is going to be e to the minus x squared, and these weight functions are basically Gaussians. And by the way, the Hermite polynomials are used to describe the eigenvalue problem of the quantum harmonic oscillator. So that's where you get all these Gaussian functions in the eigenvalue problem. And the eigenvalue lambda n is just 2n plus 1. Very beautiful, and this accomplishes a lot writing it like this, because for one thing, you know that the eigenvalues of this are going to satisfy an orthonormal relationship, and each eigenvalue has got a unique eigenvector and so forth. Now the last example I have is a very famous differential equation known as a Laguerre differential equation. It's Laguerre, which shows up in the radial problem of the hydrogen atom. So this shows up in the harmonic oscillator. In quantum mechanics. And the Laguerre polynomial shows up in the radial hydrogen atom. So the hydrogen atom, it turns out, can be separated into radial and angular parts. This is something that we'll learn in later videos when we study spherically symmetric problems. But right now, I just want you to think of it as just another differential equation that can be beaten into this shape. So this particular differential equation is xy double prime plus 1 minus xy prime plus ny equal to 0 for n belonging to n with 0, just like the previous Hermite. So the solutions are known as the Laguerre polynomials. Now the problem with this is, again, you cannot immediately guess how to write it in the Sturm-Liouville form, so we have to massage it to that form in the same manner as we did the previous problem. So we multiply it by a weight function. So again, we'll write, let there exist an f such that I'm going to write fx y double prime plus f times 1 minus x y prime plus nfy equal to 0, and that it should look just like the standard Sturm-Liouville form. So that's r y double prime plus r prime y prime plus q plus lambda p of y equal to 0. Now what we're going to do is, as in the previous problem, just identify the two sides. So I have to get f times x equals r, and also I have to get f times 1 minus x equal to r prime. But if r is equal to f times x, then r prime is equal to f prime x plus f. So now we have another differential equation that we have to solve. So the left side is going to give me f minus fx, and the right hand side is going to give me f prime x plus f. Observe the f cancels out, and now I have a nice separable differential equation as always. So actually even x cancels out. If I cancel out the f's, I can then cancel out the x's. So this is going to be very simple. Df over f is just going to give me negative dx. So the solution to this is f equals e to the minus x, right? Because natural log of f is just equal to minus x. So then I get the Sturm-Liouville form immediately. So the Sturm-Liouville Laguerre theorem is that e to the minus x yn prime prime, now I'll put theyn's eigenvalues corresponding to eigenvectors n e to the minus x yn equal to 0. So that's the form in which you write it. So that satisfies the Sturm-Liouville form with r equals x e to the minus x, the function q equals 0, the weight function p equals e to the minus x, and the lambda nth eigenvalue is just the integer n. So in this way we can write this also as a Sturm-Liouville problem, and we have the orthonormality assured from the Sturm-Liouville theorem.